I would like to welcome Dr. Daniel Fernandez, who's going to talk about coastal fog and its importance to regional ecosystems, something that's been talked about a lot recently. Professor Daniel Fernandez has been teaching physics at CSUMB for the past 26 years and is a faculty member within the Department of Applied Environmental Science. He also has been and currently is involved with a number of sustainability-related initiatives on campus, including running the Sustainability City Year program, which is pretty cool, which partners university classes with regional municipalities to promote enhanced regional sustainability. He's also working on a project with the Aquarium, Artists Link, and with other researchers on a grant that addresses the integration of art and science into curriculum designed to look at the impacts of plastic pollution, climate change, and agricultural practices on human health. He started his research in fog and fog water collection around 2005, and since then has collected fog to measure its abundance from sites across the state. Will you please welcome Dr. Fernandez?
Well, hello, everybody, and good afternoon. Thank you for sticking around to the end today. I'm glad to be here to talk about my passion, which is fog research. And when I was asked if I could present at Whalefest, I realized fog and whales, there is some overlap, but I wasn't completely sure what it was. So I took some time to think about that, and I'm going to, towards the end of my talk, I will first highlight my research, and then towards the end, I'll talk about how fog and whales actually do overlap. There is some overlap there, quite a bit actually. And I appreciated the previous speaker's remarks. Some of them are relevant to my talk, including whale poop. So I'll get to that a little bit later as well. Can't get away from that. But I wanted to start off on this opening. Hopefully on the slide you can see evidence of whales in photos and in art taken of people who are producing artistic imagery or seeing imagery in the sky. The left one is a whale tail in the clouds. If you couldn't tell that, just want to make sure you saw it, because you might, it's clouds, so you have to interpret it. And the right one is artistic interpretation of clouds in the shape of a whale. And so you'll see a little bit of evidence of that. Yeah.
Wasn't that one on the left just a flute?
Good one, Chris. All right. Whale puns, yeah. So I'll go through, here's an outline of what I'll be talking about to some extent. I'm not going to go into too much depth given the time. I don't want to, I can talk to you, those of you who are interested more after, of course, if you want to get into more details. But I'll go through really my relationship with fog. I didn't get my PhD doing fog research. That came later. I'll talk about what is fog and why is it important. In addition, I'll talk about how we can collect fog water, which is what drew me in to the idea, and different methods of measuring the water that we collect, which may not be obvious to everybody if you haven't collected water before, but it's used by everybody, and you'll see that later too. I'll talk about the network of fog collectors I've created and show you some data and talk about some mesh types. I brought a couple with me. And other methods of measuring fog, and also talk a little about chemistry in fog, which will get us kind of geared up for whales. And finally, a little bit on whales and fog is how I'll end the talk. First of all, I got my interest into fog actually at a meditation retreat, which is an interesting story. My research is not fog. I was a professor at CSUMB. I've been there a long time, over a quarter century. It seems like a really long time. And then at one point I was at a silent meditation retreat for 10 days where it was really hot and there wasn't a lot of water. There was plenty of water, but it was really hot. And I was trying to cool down. I just started thinking about fog and water and Monterey, and the fact that we have water issues in Monterey, but we have plenty of fog. And I started thinking, I wonder if we could get some of that water out of that fog and use it for something. And maybe nobody's ever thought about this before. And I was completely wrong. You can get water out of fog, and people have been thinking about it for thousands of years and doing it. So great idea, but not original. I did connect, though, from that with a nonprofit doing this work. They were very helpful in getting me started, and I became a fog researcher. Now I have fog collectors all along the California coast, particularly around here. One thing I wanted to point out about fog, what is fog? What's the definition of fog? And from the opening slide, you might have gathered that fog is related to clouds, and indeed it is. One definition is that it is a cloud that is in contact with the ground. And that's precisely what it is. But there's other definitions too. Another one is that it reduces visibility to less than 1 kilometer. If it doesn't reduce visibility by that much, it's not considered fog, it's considered mist. And then there's, of course, haze, which is not necessarily, it's similar, but it's not as big as, the droplets aren't as big as fog. Fog consists of water droplets. So do clouds. And those water droplets are typically, for fog, between 1 and 50 microns in size. And the width of your hair is probably around 100, depending on your hair, if you have any. In my case, I don't have much. But it's on the order of 100 microns. So that gives you an idea of how many droplets of fog could fit across a diameter of hair. You have small fog droplets and you have bigger ones. And if you get enough of them in the right sizes, you're not going to be able to see very clearly from one side of the room to the other. Then you have a nice thick fog. That's what gets me excited, actually, because I can collect water from it. But one of the errors I see often in fog is that I've seen this definition. They use the word vapor, and it really gets into our lexicon. Fog is not water vapor. Fog is droplets. Those droplets formed because water vapor condensed. But before they condensed, it was not fog. So fog is liquid water. So we often say, oh, the fog condensed upon, and I was taught to cringe when that was said, because I used to say it too. Fog doesn't condense, it's already condensed. So it's liquid water, and we catch it when those water droplets collide with something. It's that simple, really. And I mentioned the droplet sizes, and there's a picture of a human hair, and a couple typical, maybe on the smaller end of the size spectrum of the fog. 2 microns is pretty small. I often see 15, 20 microns in a lot of the data I look at, and I'll talk about how I measure their sizes later. When you compare it to like what we're hopefully getting today, maybe we'll get a little bit more. Rain, much needed. We haven't gotten much, obviously, in the past few years. It's called a drought. The droplets from rain are much, much larger than those from fog. They contain a lot more water than fog does. And this gives you kind of an artistic rendering of maybe fog droplets compared to rain droplets. Rain can be much, much larger, as drizzle is too. Drizzle is not as big as rain, but it's a lot bigger than fog. So it gives you some idea of, you can divide precipitation into the different sizes of the water droplets. And fog is on the smaller end. And there are also quite a few different types of fog. And I'll just mention a few of them here. The kind that we're most familiar with in Monterey is the advective fog. Or it can also be called, I guess, marine fog, perhaps. But it typically is associated with a cold ocean and warmer air over the ocean. And all of these types of fog, to be formed, they have to be created because of a difference between something warm and something cold and moisture. And so the cold air or the cold water or whatever is cold is going to cause, when you get cold and warm coming together, that's how you get storms too. It's where you get dynamics. That's where you get weather. It's also where you get fog from. Fog, as I mentioned earlier, happens when water vapor condenses. It condenses onto tiny little droplets, tiny little particles that reside in the air that are there almost all the time, especially near the ocean where we have salt spray and other things like that. You got, that provides a surface that water can condense upon if you get what's called dew point reached. So when you have dew point, that means that the air is cool enough that the water condenses out of the air, there's the condense word, and will condense onto a surface, such as a nucleating particle, like the salt from the ocean, or other particulates that are in the air, especially around pollution. You can have fog around pollution. We often call that smog. It can also be called haze. It's a huge issue in some places for pollution, but it involves little particulates with maybe a tiny bit of moisture on them, or almost no moisture. Get more moisture on them, then you'll have different types of fog. Now, not all fog is pollution. Some of it could be caused by it. And there's all sorts of science that we can talk about regarding the types of fog caused with different types of particulates. But other types of fog that are of interest, particularly when I talk about whales later, believe it or not, this is kind of interesting, but orographic fog, second one down. Orographic means it's formed because the air actually rises by a mountain, and when it rises, it cools down because there's less pressure, the air gets cooler, and so more water is going to condense out of the air because cooler water can't hold as much water vapor as warmer water. So when the air gets cooler, more of it's going to get squeezed out like a sponge in a way and squeezed out onto those little particulates. So that's why in mountaintops you typically might have clouds at mountaintops, which is fog if you're standing at the top of the mountain. It's because of this orographic situation. And if you have a situation like where you have mountains, then you also have radiation fog. Those of you maybe from the Central Valley have experienced the Thule fog, which is also a result of a difference in temperature between the air and the ground. And when you have this happening, the ground can be warmer, the air can get cooler. You can get water vapor that, again, condenses into this fog that can be very thick. It typically doesn't happen. There's not a lot of wind with radiation fog. It's very still, and it's very dangerous. Those of you driving, you can't see in front of you. It's a huge hazard. So knowing more about when that's going to happen is certainly of interest. Steam fog is kind of the opposite of advective fog. That's where you have a warm ocean and cold air. And so you might experience that sometimes if you see a warm lake and then a cooling that comes on top of it. You might see like little wisps of fog occurring over the lake. I don't know if you can really call it fog because it doesn't limit visibility to less than a kilometer, but the idea is there. That phenomenon is fog. If it expanded, it would be considered steam fog. And then ice fog and freezing fog. Ice fog is when the droplets actually freeze when they're in the air. And freezing fog is when they're water droplets, but when they hit, they immediately freeze, kind of like freezing rain. And then there's even other kinds of fog that can come up. This is one here. That is fog. That's kind of cool. I thought it looked kind of like a whale, so I put it in here. But it's a small Italian town in a sea of fog, so there's a little resemblance there in a few ways. But this type of fog, I mean, if I didn't know any better, I'd say it was radiation fog, except for the fact that I think it was happening, the air, I was told around that, I think it was in Colorado or Arizona. It was probably about 95 degrees. You're not going to get fog then. So what is that? And it actually had hailed. This was hail fog. Pretty rare. But there was enough hail that hit the ground and a temperature difference between the cold hail, which is frozen, and the warm air, that fog was formed. Same phenomenon, but kind of a rare type of fog. What's interesting, of course, is can we predict fog? That would get people very excited. And we've tried. We still try to predict fog. I hear it on the news, like, patchy fog. And that's the kind of prediction you get. But we don't know exactly when and where it's going to happen. We know it might happen, probably tonight, but we don't know when and where. And that's something that's of interest, is predicting it. And so how do we predict it? Well, we have to know what causes it. So I'll tell you in a moment or two what are the things that cause fog. You have these little, as I mentioned, these little nuclei, these little tiny particulates in the air that vapor can condense upon. Now the water vapor here, I don't want to shine anybody's eye, but it reflects there. The water vapor are these little blue droplets. And what happens is these droplets, when they reach what's called saturation, where they want to get out of the vapor phase into liquid, they need a surface to attach to. That's where they will jump onto these water particles. These nucleation particles, creating tiny little droplets of water. And that's the process, and it can be called deliquescence or condensation, depending upon some of the details of how the water reaches those nucleation particles. But if enough do, then these particles actually, they're almost like little critters, they scavenge the water vapor out of the air. And bigger particles scavenge more than littler particles, and the size of the fog droplets is somewhat dependent upon the number and size of the particulates. So the scavenging is a whole interesting process that takes place. That's really hard for us to quantitatively determine exactly. So it makes it harder to really finely predict fog. So a lot of what I do is make measurements in a lot of places and try to learn more about how is fog coming, what are the conditions associated with it that maybe we can use to make better predictions of fog. And I'll get to, so why is fog important? This is a pretty picture of some fog occurring associated with actually a volcano that actually caused the fog to dissipate because the heat of the volcano caused the fog to burn away, basically. So fog is important. This is a picture of one of my fog collectors. It was actually supposed to be a little bit later, but this is how I measure fog, and I'll talk more about this in a little bit. Standard fog collector, and I brought a little model of one here, and I'll spray it with water so you can actually see how these collect fog. But one of the reasons that fog collection is of interest is that it potentially can be used for direct human consumption. South America, there's places that have done this: Chile, Peru, Bolivia. There's other South American countries where fog water collection is taking place, Guatemala, Central America, but where large fog collectors have been set up for the purpose of providing fog water for human consumption. I visited a village in Chile that did that for 9 years. They collected water from fog. Fog up on the mountainside, the orographic fog. They're in a fishing village. They had no source of well water because they were right on the water, and they were 30 kilometers from the main highway. They had to truck their water in. They decided to set up these fog collectors on the mountain, at least a non-governmental organization did for them, and that lasted about 9 years until they decided it was just too difficult to maintain. But it was interesting. I visited that village and saw some of what had been. Here's a picture of, I would call this probably not a large fog collector, but a medium-sized to large fog collector. You can get bigger, get about 50 square meters. I'd say each of these maybe 15. The sum total of them is pretty large. But this looks like it might be in Morocco, where there's a large installation, currently the largest in the world, of fog collectors for collecting water for human consumption, providing about 40% of the water for 3 villages, a little over 1,000 people from fog. There's a large fog collector, the only one, that I set up with some collaborators at Fort Ord Natural Reserve. It took some doing, and I learned some things about what not to do. But that was a large fog collector, 50 square meters, and it was up for a couple months before a moderate wind blew it down. But also use of fog for agriculture. Can fog provide moisture to make it useful for growing things? That's certainly of interest. And also not only for growing things, but sometimes fog is a problem for some crops because it can produce molds and other parasites that affect plants. So understanding that is important for the ecosystem. There's a relationship between fog and ecosystem. It can be both positive and negative depending upon who you are and what you're interested in. Landscaping, xeriscaping. I was talking actually to somebody from Catalina Island, for instance, where they're trying to reforest there. They removed, I guess, the wild boar and the goats that had maybe consumed much of the landscape there, and they're trying to grow more things there. And they want to try to capitalize upon using the fog to help grow, not for agricultural purposes, but for reforestation purposes. Because trees are actually natural fog collectors. But if you don't have the trees, you're not going to collect whatever fog forms there. So trees are an important part of the cycle of the fog ecosystem collection. But if you don't have them, can you maybe simulate them for a while until they grow enough to start collecting their own fog again? This was done in Spain, for instance. There's an example where they're trying to reforest with fog collectors. And there's other plant species that are thought to be somewhat dependent upon fog. Certainly redwoods are an example of that, but there's other species as well. Manzanita and other species of plants, and some fauna as well, are dependent upon not only the fog, but the temperatures associated with fog. So if fog changes due to climate change, what's going to be the impact on those ecosystems is an important question. And of course, we're interested in fog whether we know it or not. If you look at energy use here, you'll see the lowest energy use tends to happen along the coast here. I'm reflecting. I don't know if I'm getting it. I'm getting it on the wall. I don't know how much I'm getting there. But the blue areas here along the coast refer to lower energy use counties, partly because less air conditioning needed. You get the natural air conditioning associated with the fog and the marine layer. And there's a little graph showing that, typically the coastal counties are the ones that are lower energy use. And the coastal counties are the first few that I have plotted there. This is back in 2016 data or something like that, but this similar numbers would apply now. Similarly, water use tends to be lower in coastal regions, partly because it's less heat, so for growing purposes, you don't need as much water as you do in areas where it's hotter, but also perhaps because there may be more moisture associated with fog, so there may be slightly less demand for water use if we are able to track that. Can also affect airport landings, San Francisco Airport. My first take on fog water, or interest in fog collection, was from folks at the San Francisco Airport who wanted to be able to better model the impact of fog on flight arrival and departure times, because it was affecting San Francisco Airport. Money talks. A late flight, delayed or arrival, affects everything in the country, of course, and airports are expensive. We're talking, every minute is that a flight's delayed costs them who knows how much. So anything they could do to better understand the fog, because there's actually 2 narrow runways in San Francisco, and if it's foggy, they can only use one at a time for safety reasons. So that's the reason there. So there's other airports that may be true for too, but San Francisco, certainly. I'd say, why don't you build another runway? That's expensive too. So they'd prefer less fog. I'm certainly not necessarily of that ilk. And there's what I think is interesting, about fog. This is more about ecological consequences. Fog's different from rain. If you go out today, I biked here this morning. I had to do something at the aquarium, and then I came right here. It was perfect setup. But I'm biking, and it's raining. Underneath the tree is dry, right? When it's raining, it's kind of nice. It wasn't raining hard, but it was raining enough that underneath the tree, I get a little bit of shelter from the rain. When it's foggy, underneath the tree, you're going to get wet. All right, so there's a difference in how the water manifests, whether it's fog or rain or drizzle, for that matter. Those are going to be coming down. Fog doesn't fall. It blows this way if you have some wind, accumulates in the tree, and then it drips down. So it's kind of almost an inverse if you look at the ground pattern. If you're wondering, was that fog last night or rain? Look at a nearby tree, and if you can see the ground beneath it, is that wet underneath the tree or is it dry? That'll tell you something about maybe which one it was. And there's also a relationship between stream temperatures and fog abundance. And of course, when streams get too warm, fish tend to die in them, depending on the type of fish, but trout prefer a certain temperature range. So we're seeing that fog can be a moderator for fish species, and certainly in coastal streams. There's some pictures of people catching them. And then there's certainly literature, if you're interested in, how fog can possibly also be affecting stream flow. Not that the streams are necessarily flowing fog water, although some of it might be, but when fog occurs, some of the fog is absorbed actually through the stomata of some of the leaves of some of the trees. We've seen evidence of that from some of them. That's not exactly my area of research, but I know that is the case. And it also reduces evapotranspiration, which I think is the next slide here. So when the tree leaves get wet, they evaporate less water, basically. So they draw less water from their roots, which leaves more water in the streams. One interesting thing is after the fire in Big Sur a few years ago, a friend of mine who had a house said the streams were really full because there were fewer trees. The trees weren't sucking the water because they were burned down. And so the water levels got higher in the streams, which was odd at first, but it makes sense. The same kind of thing can happen with fog in a much less damaging way. If the fog's in the leaves of the trees, they're not going to evapotranspirate so much. They'll still be alive, but they won't necessarily draw in as much water. There are also chemicals in fog. Fog is a vector. It can carry things. And that's actually one of the things I was going to compare fog to whales. So I'll give you a little sneak preview of that one. Fog sits around, right? It sits around. It doesn't fall very quickly. It falls maybe at the rate of, depending on the size of the droplets, millimeters per second. It's basically sitting there. It's called a colloid. It's like putting cornstarch in water. It doesn't all sink to the bottom. It kind of sits there. That's fog. That means that if there's something in the air, the fog can pick it up. And if there's wind, the fog can possibly blow it. And it's absorbed within the water, and it can be brought to somewhere else. And that something can be chemicals, can be industrial chemicals. It can be natural chemicals from the oceans, sodium, chlorine, sulfur from the ocean, potentially. It can be mercury, as methyl mercury has actually been seen in fog, particularly coastal fog. Not huge amounts, so don't worry. Don't worry about stepping out in the fog if you're close to the ocean. You won't get excessive mercury exposure, more than you're probably going to get anyway. We're talking 1,000th the concentration of that in tuna. So that's often something that gets misunderstood. So, but fog can carry it, and that can have ecosystem and food chain implications. Fog can also harbor bacteria. They can be the little particles that the water condenses on. They can be the nuclei, can be bacteria. So all of that can be in fog. It can also be in rain, too, because fog eventually becomes rain. I think maybe fog is when we think maybe rain's grandfather, because when the fog droplets jiggle around in clouds, or the cloud droplets do it, that's where they coalesce and become raindrops and eventually get upon. That something is going to be in rain or fog. So you probably want to purify it before you drink it. That would be my recommendation. And there is potential evidence that fog is being affected by climate change. This picture doesn't exactly show that, but it shows really an interesting phenomenon of fog being generated by large-scale wind turbines off the coast in a certain area. I think this is off Denmark here, which is pretty fascinating. Actually, I was contacted by somebody from a reserve down by Cambria, where we're looking at doing an offshore wind farm here. And they were concerned that the presence of the wind turbines would reduce the fog. And so they're bringing it to the city council and all that, and they asked me for research on it, and I don't really have much. But I did a little work, contacted some friends, and I at least got some pictures. This is not peer-reviewed, anything like that, but it does show evidence that perhaps fog can actually be created by wind turbines. And a little left brain relief, because we've been talking a lot. So it's a little haiku I wrote. Behold the fog around us, swirl, churn, captivate, a source of moisture. And there's a picture of orographic fog. You can see the mountainous area there. This is how I measure fog coming from the standard fog collectors that I showed you just briefly a few photos before. So what those are this. And I'm going to do a little demonstration here. There's nobody right here, so you won't get wet. So if I spray this here, this is just a spray bottle. So I'm going to spray. It's not really fog. It's probably larger droplets than fog, but the idea is there. If I spray this enough, I got to turn it on so I can spray it. I turned it off so I wouldn't spray myself earlier. I want to do it somewhere so it atomizes it a little bit. No, not like that. There we go. So it's kind of a spray. And eventually, the water, you can see it from a distance, it starts to coalesce on the, this is polyethylene mesh. Unfortunately, it's plastic. But it is effective in terms of catching the water and then not letting the water stick to it. It's called hydrophobic. And you can see the water starting to drip down. Trees do the same thing, especially tree needles like redwoods. But as I spray this here, the water collects on the mesh and starts dripping down. It's dripping down this. This is typically at an angle, and I won't pour all over your carpet here, but then the water will just flow down the gutter. I make the gutters at an angle so that it can be collected and measured down here. And that's what I do. So the measurement of the fog happens with something called a tipping bucket rain gauge. I didn't bring one with me, but basically it's two little buckets inside. When one of them is raised and the water enters it, it gets heavier, it tips. Then the other bucket is ready to catch the water that drips down from this little hole in here. And when it gets heavy enough, it tips. By counting the tips and knowing the volume per tip, I'll go over here. By counting the tips and knowing the volume per tip, you can determine the amount of water that you've collected over whatever period of time you're interested in, whether it's a day, an hour, a month. I have all the data. I record the time of every single tip. So if you want to know what time it tipped, I could tell you that. So that's basically how I get my measurements. There's an example. I actually calibrate all my rain gauges, which I find important. A rain gauge, by the way, whenever you see it, I mentioned this earlier, meteorologist report, which is telling you how much water has been, you can look at the meteorological report tonight, how much water has fallen. You'll see something like maybe 0.02 inches, 0.03 inches, something like that. It always bothered me. How do you measure an inch of water? Why is that a volume? 0.01, 0.02 inches? Why is that? That's a length. But we're treated as a volume. And I just want to point out why we do that. It makes sense. because when it rains, everywhere supposedly in the region has 0.01 inches of water that fall on it, or let's say 1 inch. So if you, like this room, if this room had an open roof, which it doesn't, and it rained and you get an inch of water, that means everywhere in this room would be an inch deep. So the volume would be multiplying the area of the room by that inch of water. Then you get the volume. Of course, the bigger the area you have, the bigger the volume you have. So for meteorologists, going with 0.01 inches, 0.2 inches, that makes a lot of sense. When you're a fog researcher, it doesn't make sense. Although I've seen plenty of papers that talk about how many millimeters of fog fell, but that doesn't make sense because fog doesn't fall. Fog blows this way, and you measure a volume. So I'm interested in the number of liters I collect per square meter of collection area per day or per hour. That is a useful measurement. So it's a different type of measurement than with precipitation. And you can't directly compare the two because precipitation falls everywhere. Fog doesn't really fall much. It hits vertical surfaces, and you collect water off that. And so it has a different mechanism. So I thought I'd mention that. But every bucket also measures a slightly different amount of water causes a slightly different amount of water causes the bucket to tip for different buckets. So one of my huge jobs in my research, and I have probably over 100 buckets that I've used, is to calibrate them every year. Check, do I still have the same amount of water per tip that I had a year ago? So I devised a system to do that, and that's what this is. It delivers a rate of water very slowly. It takes about 20 minutes. About a half liter of water, I measure the number of tips, I get a value for calibration for the bucket. And you can see it varies across buckets. So that's something I learned. Different buckets, different calibrations. And I mentioned rain and fog in the units just a moment ago about inches versus liters. That's really what a point I wanted to make. Because I've had people contact me and say, wow, from fog you get 0.2 inches of water. That's incredible. I said, no, you're measuring it wrong. We're talking a couple liters. Don't pretend you're going to get that much water from it. That's wishful thinking. Much as I'd love to if we could, it's not what you're going to get. You're going to get a small amount compared to what you think you're getting if you're using the way meteorologists measure water from rain. So what I have over the years, this represents locations where I've had fog collectors deployed all the way from Northern California up. Let's see, I'll go here. Can you hear me? Can you hear me? Yeah, they can hear me. From Northern California, whoop. I thought I had a laser. Oh, there it is, sort of. Okay, from Northern California up here, there's Northern California, all the way down to the Mexican border. I've had fog collectors at times. I don't have them going continuously at those sites now, but I've had them at some point in the past decade. Most of my fog collector work is centered around Monterey Bay right now, although I do have some at some other locations. But I have over 30 within a couple miles of the CSUMB campus. Which are collecting regularly, which I'm using for various research projects. And they also look good on campus. I'm using them to water oak trees. It's kind of fun. So that's a little bit of what I have in my current network. And this is a poster, I'm happy to share it, that shows, this is 2019, that shows a summary of some of the monthly totals of fog data that I've collected over the years. And some of the sites where I've collected more, some where I've collected less. It's interesting because it's not uniform. I think if there's one outcome of this talk, the amount of fog you're going to get in one place is not the same as the amount of fog you're going to get in another place, even if the places are pretty close. Even a few meters apart, they may differ over time. And it's hard to know that just by looking at the place. But I can see it in the data. It also can vary year to year. Some people have asked me, is the last 10 years, has the fog pattern changed? Well, we've had good fog years, heavy fog years. This is from a site on campus, CSUMB's campus. 2011 was a particularly good year for fog at that location, and many locations, Central California. If you remember 2014, 15, those are really bad fog, beautiful summers, not great fog years. We did not get much fog. We also had a drought those years, for whatever it's worth. Does a drought imply less fog? Not necessarily, but we had less fog those years. But then I don't have more recent years, but it popped back up again. And this is for August. This is during the month of August, which it used to be considered fogust. We used to think of August as a foggy month. Well, sometimes it is, and sometimes it isn't. And more recently, the past few years, I've actually seen more fog in August than other years. So there's variability associated with fog. It's not a linear relationship. It's just increasing or it's just decreasing. There's a lot of variability. On the whole, I would argue it's probably based upon other reports of people who have measured fog over the years and other papers I've seen, I would argue that fog is probably decreasing as a result of climate change. And that matches a lot of anecdotal evidence I've heard too. But I don't really have the evidence within my own limited data set to say that. I'm relying on data I've seen from other researchers too. And this is kind of fun. These are fog collectors that are deployed on CSUMB's campus. If you ever visit our library, Tanimura and Antop Family Library, and walk behind it, you can see 10 fog collectors that I actually deployed with a class as a class project to water sapling oak trees. They were going to stay up for 2 years or 3 years. It's been 4, and they're still up. I'm going to have to fix them every now and then. And I calibrate the buckets every year, so it's a big job. But there's the class that helped me deploy them. And I'm happy to say they're all 10 of them are up right now still. So. And as I mentioned, there's a lot of variability. This is just from the first few days of when I collected water from them. But this is just within an area of about an acre. Some of them collect twice as much fog water as others for reasons I'm not fully sure on. And I want to do more research to look at the wind patterns in that little area where I collect them, because I think it has something to do with the way the wind blows and how it hits the different fog collectors. But it's fascinating how much different the fog collection from some of the collectors is than from others. And this is just over a period of a few days in this plot here, but I have years of data from these now. And I also am looking at the effects of different types of mesh. Are some mesh better at collecting fog than other types of mesh? And this is a big area of research because you'll see papers from some researchers saying that their mesh is 10 times better than any other type of mesh. I've seen it. And that may be true at a certain size droplet of fog, but fog exists over a large number of droplets. And so whenever I see something that looks that good, you know what they say, you know, when you get an ad for a car or something, it's like, it can't be that good. There's probably something up there. Same thing for fog collection, I think is true. You might get 20%, I've seen that sort of improvement in mesh, different types of mesh. But when you're talking orders of magnitude, it's actually not numerically possible because the mesh that I use are about 30% efficient or so. You can't do more than 3 times better, and you're never going to have 100%. So keep that in mind if you're looking at mesh efficiencies. But that is a big area of interest because we're interested in getting what water we can from fog at times. And it's good to know, are some mesh better at doing it than other types of mesh? And this is a paper that addresses that. And there's going to be another one coming out soon that's using a different device, which I'm going to talk about right here. This is a device called the FM120. This device measures the size and the number of fog droplets in the air. These devices are my standard fog collectors that I mentioned earlier that I showed you this here. There's a little demonstration model of one. Whoop, there goes the water. These things here actually measure and count the droplets. So this is like how you measure how efficient they are. You put one in front of the fog collectors, like this one here. You put one behind them. This is another one here. So that one had some problems, but these are the 2 newer ones. From that, I'm measuring how much fog do you have in front of a fog collector and how much behind it. In other words, how much is my fog collector actually pulling out of the air of the fog? This is the way to measure that. And this is what I'm doing right now. I just got these devices a couple years ago, and I have a couple years worth of data from them that I'm pouring through. And there's some interesting results coming. I'm really excited about it. Actually, I have a couple of the results right here. And you can see this is the amount of fog in the air. This is called the liquid water content, which basically says how much fog water in liquid form is in the air, LWC. If it's above 0.01 grams per cubic centimeter, it's considered fog. That's kind of like our threshold. And you can see 0.01 is somewhere down here. So this is a fog event I'm showing you, which is kind of exciting. I like showing fog events. So the red one is the unperturbed one, and then the green one is the one on the side of the leeward side of the fog collector. So it's basically, yes, the fog collector is taking a lot of the water out of the air, turning it into water, presumably, and you get less that's remained in the air. And that's what this graph is showing. And so looking at these ratios, you can start looking at percentages, looking at efficiencies. And there's a number of different efficiencies that have been plotted theoretically, but I can actually measure them now, which is great. And see, here are a couple of efficiencies. Some of them, one of them is actually showing 100%, which of course, if a student in my class got 100% efficiency, or even worse, 117% efficiency, and didn't say why they got that, they'd lose some points. So I look at that and say, oh, okay. 5 more minutes? Okay, thank you. And then I can start comparing things like the standard fog collector is supposed to use double layer of this mesh that you see here. But I can start comparing single and double and triple and seeing which one's actually better and in what circumstances. So I can learn a lot about the microphysics of fog collection and what makes a better fog collector and in what conditions. And this is an example of the kind of graph you can start looking at, oh, this one got a little bit better than the other one. I said I'd talk a little bit about mercury and other chemicals in fog. You can also have mercury in whales. So there's another comparison between whales and fog. But one of my colleagues noted that methyl mercury is of higher prevalence in coastal fog than in coastal rain. In other words, I mentioned that earlier, for reasons because mercury is generated by bacteria in the ocean, not mercury, methyl mercury, that basically eat the mercury and poop it out as methyl mercury. There's another poop analogy there. So that is what gets into the food chain. It gets into the tuna. It works its way up into the whales. Whales are very high in mercury. So that's a huge issue. Well, so is coastal fog. So there's an overlap there between whales and fog. And a few years ago, a colleague of mine and I worked on this along with a lot of other folks. And we did ship cruises where ships were cruising up and down the California coast trying to measure fog, trying to capture water from fog and measure mercury in it. Surprisingly, we saw the mercury more on the land than we did in the ocean. I'm going to say mercury, methyl mercury. And there's some value. You can see where the hot spots are on the coast, not in the ocean so much, but on the coast. So it's interesting. And when I say hot spots, don't worry, like I said earlier, don't worry about it. Don't worry about stepping out in the fog. Hot is relative. Still thousands of times less than mercury in tuna. And there's a whole process for how the mercury gets into the fog. A lot of chemical exchanges occurring, which I won't get into the details of here, but it happens. And these things also happen in whales. Whales pick it up too, up the food chain, right? Bacteria goes up from bacteria, the phytoplankton, it just works its way up, and the whales eat it, becomes part of them too. There's another whale tail. This was actually taken in Monterey area, so there we go. Just like so here's the whale and fog comparisons. Just like whales move materials. I said fog does, and the previous speaker confirmed that. And here's more whale poop, all right, which is a really important part of the coastal ecosystem. It's providing food and nutrition for phytoplankton. And so whales are an important part of the ecosystem. If you get rid of them, you're going to kill out your ecosystem, which is counterintuitive, but a point that's been raised already, which is very important. And of course, fog is also a vector for all sorts of things. Whale breath is fog. It's not, yeah, there's another connection. Whale breath is fog. Those spouts you see, that is fog. Whales produce fog. How do they do it, and why is it? Yes, there might be a little bit of spray of water, but it's not primarily what that is. That is fog because when the whales expand, they push out with 2 or 3 times the pressure we do. And you can create your own fog on a cold day. Well, whales can do it on a not cold day. It's like the orographic rise of fog. The water vapor in the whale breath, when it's expelled, it experiences much less pressure, just like the air that rises on the top of a mountain, that orographic fog. So that is kind of like orographic fog. That's what it is. Of course, it dissipates quickly because it's not in equilibrium like the fog that you see outside. And also, just like regular fog, whale fog, if you like, or whale blowhole, what's in it, includes bacteria. And by measuring that bacteria, we can better learn the health of the whale. So just like we can measure stuff in fog and learn about where the fog came from, we can learn about the whale from, and people fly drones over those whale blowholes to try to collect some of that water. And fog may have protected some of the whales, I'm guessing, because you see a whale from its blowhole, right? It's difficult to see whales without fog. So fog may actually provide some cloaking for the whales. So I'm trying to talk about the relationship between whales and fog here, potentially. Of course, you can hear them, too. People got good at detecting whales. And just like fog, whales can be unexpected. I'm almost done. I know we're just about out of time. But this is an example of how fog saved a town in England called, the town was Durham. In 1943, the Germans were trying to bomb Durham. And they were trying to destroy the whole thing. There was a cathedral there called St. Cuthbert's Cathedral. And because fog came unexpectedly, because they couldn't predict it, the fog covered the town, and the German bombs landed in the countryside around the town. They didn't hit the town. They saved the cathedral. The town survived. And that mist was known as that fog's known as St. Cuthbert's Mist as a result. But just like that, not only is fog surprising, but whales can be surprising too. And this is a whale in fog, as you'll see in a moment. And you should hear the people, there's sound in this, but that's okay. You just hear, oh my gosh, there's people on a boat. And this whale was doing it continually, apparently. And I'm just going to end with the song by a poem by Carl Sandburg. This is more about cats than about whales, but it's about cat's paws and fog. And I'll say it in Spanish. La niebla se viene en las patitas de gato, se siente mirando sobre el puerto y pueblo, en las ancas silencias y entonces se mueve. So he's likening cat's paws to fog, how it comes and goes. Thank you very much.
We actually have time for a couple of questions. Yeah.
All right.
So,
Happy to take them. Sure. And then.
The device that you were measuring the in front and on both sides of the mesh, is that using like optical?
Yes, it's using a laser forward scatterometer.
So it can count droplets.
Actually,
so why not use that as opposed to the
there's a couple reasons. One is it doesn't collect the water. It only measures it. So if all I want to do is measure it, great. If I also want to collect it, then I want to use the mesh too. And the other thing is my mesh, I could build one for a couple $1,000s. Those devices, fully told, about $70,000. So I'm fortunate to have three.
Yeah.
And they can tell me a lot. So I'm trying to learn from the mesh what they can show me, and then maybe use the mesh as a proxy for them in other places too.
And then also, is that how you're calibrating? Is by comparing?
No, the calibration is just the rain gauge itself. So the calibration is not really based on fog at all. It's a calibration that should be done it should be done by meteorologists if they're using the rain gauge to measure rain. It's how many tips correspond to how much water passing through. So, but the FM120 in a sense is kind of calibrating the fog collector. It's telling me what percentage of the water is actually being collected by it. So it is kind of a calibration in a different sense. So I see your point. Yeah, good question.
Thank you.
Sure. There's a question over here. Here and then here. Yeah.
I'm just trying to understand the mercury, or the mercury methyl. It's in the air and then it attaches to the fog and then gets down into the water?
Yeah, well, it actually comes, it's an interesting cycle. When we burn coal power, when we burn coal,
Yeah.
a lot of things get into the air, including mercury.
Okay.
And that eventually is going to work its way to the ocean. When it's in the ocean, bacteria that normally eat sulfur eat the mercury. They're like, oh, we have mercury, great, I'll eat that for dinner instead. They produce the methylmercury, which works its way to the surface. When bubbles pop at the ocean surface, it actually gets released. So you get small amounts of methylmercury, certainly in the water column, but also in the air above it, or in the fog above it, in the droplets. And we see that evidenced in the fog, if that kind of explains a little bit. Sure. Another question.
So for your fog catchers, is there like a certain direction that you post them, that they're facing in order to collect fog?
Good. It's a good question. Yeah, the question was, is the direction important? For the fog collectors that I have, for instance, this one here, yes. The direction has to be such that the wind is going to blow into the fog collector like this, ideally. So the thing is, wind varies. You don't always know. So what I do is I try to align them in the direction that the wind is most likely to come when there's fog. But they're difficult to move, although I am working on a movable version that will actually try to follow the wind. But that's not something you can deploy on a practical basis or a large scale. That would just be kind of out of academic interest. Yeah, good question. Yeah, please.
I don't know much about oceanographic landscapes, but how much does the Monterey Canyon influence fog?
Oh, Monterey Canyon influence fog. That's a good question. Yeah, I would argue that fog is probably going to be occurring along the ocean where you have upwelling. So when you have an upwelling spot, then you're going to have cooler water. That's going to be more likely to create a greater difference between the air temperature and the water temperature. So that would be probably the places where you would tend to get fog generated. So Santa Cruz, for instance, is typically less foggy than Monterey, for instance, because of the upwelling patterns, I would suspect, along the coast there. So so the canyon itself, in terms of how it's driven by upwelling, how the cooler water below comes up, would be an influence. Now, the specifics of the topography of the canyon, I don't know if I can say a whole lot about those in terms of fog, but that's a good question. I'd say it's related to upwelling. So if you can relate it to upwelling, you can say more about it. Sure. There was another question, though. Yeah, and then Chris, after you. Go ahead.
Just back to the wind direction one, could you not make your mesh in a cylinder so that it doesn't matter what?
That's a great question. Could I make the mesh in a cylinder? It's certainly possible. Certainly possible. The thing is, this mesh, particularly, I have other mesh that I think does it less so, will impact the wind a bit. So when it blows through, the wind changes. So if I have a cylinder, the far side is not necessarily going to get the same amount as this side. But creating some sort of an omnidirectional mechanism, there are other types of fog collectors that use vertical strings that are typically done in a circular pattern so that you do get an omnidirectional relationship with the wind. So the idea is there. Sometimes the question is, what's the goal? Usually the goal is, let's set this up so we can see if a larger fog collector is worth doing. Well, a larger fog collector should probably be planar like this. So it's probably best to set up something planar because of the difficulty associated with setting up something. You get more bang for your buck with a large planar fog collector than making it circular, if you know about how to align it, I would argue, based upon other research.